Hello Year 10 and welcome to the next of our PowerPoints. Now, I haven't marked your homework yet because this is Monday and you're still submitting it potentially, or not homework, your work on the fuels and the problems of combustion and reactions. So I will do on the next video feedback for any of the research you've done on any of the things you found in terms of the issues like global warming, global dimming, etc. And if there's anything else I've missed, because I found something I've missed already, I will put it into the next PowerPoint. But for today, we've got a new one. We are looking at organic reactions. This is a new topic. Now, this new topic is quite exciting. I quite like organic reactions. There's some decent bits here, and it goes into a bit more detail than a lot of the chemistry GCSE course, which is quite nice. I'm going to show you some cool reactions and something called a mechanism. Which you don't need to know, but it's probably worth being aware that they exist and having a vague idea what they are, just to get a feeling for what chemistry is like when you start getting a bit more serious. So, first off, what I forgot last lesson. So in the combustion lesson, the thing I failed to mention, and going through my PLC afterwards, I was like, oh rats, didn't put that in, by which time it's gone live already, so I can't edit it. So you're going to be seeing this a week after I make it. The one I've just done has gone live today, so I'll get confused about the past since you're seeing this on Monday, the one second week in July, whereas this is Monday the 29th of June for me. That was a little bit of pointless exposition there, apologies. So, what did I forget? Well, essentially, I told you all the products of combustion, but I didn't mention how we can prove or how we can demonstrate these products of combustion. And that is done through this little experiment. Now, you'll have seen this in year 9, and hopefully potentially 8, maybe even 7, because it does the chemical reactions topic in 7. They might have shown you combustion in this experiment, but I would expect it to be 8 and possibly 9, where you would have seen this most recently. So, key things. Here is our source of flame. In this case, it's a Bunsen burner, and we are testing to show that our Bunsen burner is producing 2 of the 3 products of complete, or the two products of complete combustion, and 1 of the products of incomplete combustion can also be shown with this method. So, methane in, and then up here we've got a flue, and this tube, we've got an air intake here, and this tube then connects to a U tube, yes, for the online video provider, and then that connects through here to a normal boiling tube with lime water in it, and that goes to a suction pump plugged into your tap. So air is being pulled through here constantly, so the products of combustion being made here are being sucked through into these various parts. Now, we're testing for 2 things here. The third to mention now in incomplete combustion, if you put this on a yellow flame, you'll be making soot here, and so you'll turn this upside down glass funnel very quickly black and covered in soot. So you can easily show products of combustion, incomplete combustion soot, or unburnt hydrocarbon particulates there. But the gases from complete combustion will be sucked through here, and we get to this first place here. So this first place, cold water in a U-tube. The U-tube is there to allow the gases to be pulled through, and the ice bath is there to condense the water. So any water vapour coming into here will get cold, condense, and then form at the bottom. Now I've added this detail, cobalt chloride paper. You can use anhydrous copper sulfate, which will turn from white to blue in the presence of water. You can just not have anything in there, and have it just, you can see water collecting, and then you can test the water separately. But I like the cobalt chloride paper. It actually makes the ice bath very redundant. But that cobalt chloride paper starts out blue, and when you add water, it turns pink. And I can actually show you that equilibrium when we get back into lab and we're doing equilibrium shaped things, because they're probably worth revising, because equilibrium always requires some revision because it's nice and hard. Okay, so we've tested for water here using an ice bath and some cobalt chloride paper, and the remaining gas is then sucked along here and passed through lime water. Now, hopefully you'll recall that lime water is the test for carbon dioxide, and so with any luck, that will turn cloudy. Okay, so that's how we tested the products of combustion. And like I say, I just forgot that last lesson, so apologies. Now, today's lesson we're looking at the reactions of alkenes. And this is the first lesson in the new subsection of the reactions of organic chemicals. This is triple only, so if you happen to talk a lot to any combined scientists, they will not have a clue what you're talking about if you get into this bit. So, first off, alkenes are slightly different to alkanes. Yes, they still burn well. Yes, they are more volatile, but actually there's a neat little trick in their chemistry. That means they don't actually burn as well with oxygen. Well, they don't burn as well, even though they're more volatile. They don't burn as well, and that's because their double bond is highly electron dense, and oxygen is pretty electron dense. And so it just makes the actual mechanics of the interaction required for burning a little bit harder, and means that alkenes are a little bit less likely to burn completely, and so they tend to burn with smokier flames. So this means we get more incomplete combustion, and we release less energy per mole than the alkanes do. This is why generally we prefer to use alkanes rather than alkenes as fuels. That and the fact that alkenes are so much more useful for everything else. So, here's an example of complete combustion. There's ethene plus oxygen, making carbon dioxide and water. We did loads of those last lesson, so, maybe next time. Okay. I've got a little 4-mark question for you here. What I'd like you to have a go at is, having looked at that previous slide, can you give me 4 bullet points or 4 marks of why somebody might prefer to use octane rather than octene in a car? This is of course a petrol car. Pause, have a go, answer shortly. Hopefully you unpaused and have got 4 marks worth of answer. Here they are. So, tends to undergo incomplete combustion. You don't need to talk about the double bond being highly electron dense, don't you? Oxygen normally acting as a nucleophile, that's all A-level stuff. But I thought I'd give you a little explanation because I don't really like just rote learning things. So octene tends to undergo incomplete combustion. Therefore it produces a smokier flame. That one, I can understand why you might not have written that one. It's true. In terms of disadvantages in the car, the only reason that's a disadvantage is because you're going to be producing more products of incomplete combustion, which could be harmful to the environment or to people. There we go, it mentions that next. This produces more CO, which is poisonous, and more particulates, which are a problem as well, but I haven't mentioned those in the mark scheme. The key ones are octane releases more energy per mole during combustion than octene, so it's more efficient fuel. I'm going to assume that you might have written that the other way around as well, in which case octene releasing less energy per mole than octane. Fair enough. Of course, having one less water molecule being made is probably a significant reason why you get less energy. Right, moving on. So, the next interesting form of reaction that the alkenes do, because we've done combustion a lot already, are addition reactions. Now, I mentioned these in passing when we did our alkenes introduction during the cracking lesson, and this is where they're fundamentally brilliant. So we talked about the whole double bond being electron dense. It's got a lot more electrons in that space than you'd really expect it to have, because rather than just having the 1 electron pair, the double bond in fact has 2 electron pairs. Don't know why I chose to draw it like that, pretend I didn't. So 2 pairs of electrons makes that double bond particularly electron dense. Okay, so this means the double bond is able to open up, and therefore we can add things into that molecule, which we call addition. Now, you have to know quite a few different addition reactions, but before we're going to look at one example and we'll have a look at the mechanism. You are not required to know any mechanisms at all at GCSE, but I just find it makes understanding what's going on easier, and therefore, because you don't otherwise, you just learn it, and therefore I think it's probably quite useful. So let's have a quick look at an example. First off, the most obvious addition reaction is the halogens, and we know they react with the halogens because, of course, this is the test. The halogen addition reactions are how we test for alkenes. The bromine water turning colourless is that key indicative test you must recall. So there we have orange bromine water with an alkane, colourless bromine water with an alkene, because it's not bromine water anymore, it's just water, with a now halogenized alkene, so an alkane, haloalkane. Okay, so there's alkane with bromine water, and there it is with alkene. You probably recognise this from the other PowerPoint. Okay, so these will also react with chlorine, bromine, and iodine. We don't need to know about fluorine, thankfully. So, no, it says also, because that's bromine. Didn't correct that again. So, what would you name these molecules? Now, bear in mind, you don't really need to be able to name these properly. Nomenclature of these things is not required at GCSE, but your exam board can be a little bit mean, so let's have a quick look. I'm trying to remember exactly which one you have to name. So we have ethene, I'm going to put bromine onto it. Now, that double bond is going to break open. I'm going to add a bromine molecule onto each side of the carbon-carbon double bond where it was, and this will form us an alkane with 2 bromines. Now, so far we've only called things alkanes and alkenes. Is this going to be an alkane or an alkene? Well, is it saturated? Yes. I've only got single bonds. A pen. Single, 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 single. So it's no longer an ene. We've turned an ene back into an ane. But it's not a proper ane because we've got these functional groups, these bromines stuck on the end. So how are we going to name that? Well, we give it a slightly funny name of bromoalkane. Now this is, as we said, this is an ethene, so it's going to become an ethane. And it's going to be a bromoethane because it's got bromine. But even more complicated, because it's got 2 bromines, we use a little prefix to say how many bromines there are. So this is a dibromoethane. There you go, dibromoethane. And this just shows off the wonder of organic chemistry, because this whole thing is, this name is just Lego, and if you know the structure, you know the name. Any name of anything in chemistry that's proper organic is going to have like this Lego brick name. So the di just means 2. The bromo means bromines, so 2 bromines. Then we have the eth, which tells us how many carbons there are on the main root. In this case that means 2 carbons. And then we have the ane. Sorry about the horrible writing. And the ane just tells us there are no double bonds. So literally all that name does is, as a series of pieces, you stick them together, you make this nice little Lego name where you've got the name of all the bits and how many there are. And actually when we go on to proper chemistry at A level, they've even got ways of telling you where they are. So the proper name of this molecule is 1,2 dibromoethane, because this bromine is on the first carbon and this bromine is on the second carbon. So dibromoethane, you don't need to want to, you don't really need to be able to name those, to be honest. Okay, that would of course form a colourless solution if we were talking about bromine water, which begs the question, why doesn't it say orange over there? I'm not going to write orange because that should be childish. Oh. Oh, almost looks like I went through this PowerPoint beforehand. Oh no, you know what, I did. I added orange, because it didn't say orange originally, and it made me cross, so I added it. Oh well. Now I feel a bit silly. Okay, next slide. Avoid watching me just randomly rub things out. So, this is the proper exciting chemistry, and if I was in lab, I'd be getting a little bit excited, hopping from foot to foot and drawing lots and lots of mechanisms on the whiteboard and rubbing stuff out. So unfortunately, I have to make do with a whiteboard pen and my not physical presence to get excited about this. But here we have the proper mechanism for addition reactions. Now, one thing you'll never have seen before are these curly arrows. Now, these curly arrows are totally and utterly confusing until you're told what they are, and then they make complete sense. They represent the movement of a pair of electrons. We draw a curly arrow with a double head for 2 electrons moving, so a pair, or a curly arrow with a single head for 1 electron moving. Again, this is way beyond the scope of GCSE. So what's going on here? Let's have a look. So first off, this is the bromine molecule, this is the halogen molecule, and at complete random, sometimes one end of the bromine molecule, and I'd be waving my hands around like a crazy person here, so try and picture that. The electrons in this molecule are sort of randomly distributed, but they're electrons, they're super fast, and they move all the time. So any given millisecond, they might all just so happen to be at one end rather than the other. And if they're all down the bottom end, here, then this one becomes slightly more negative because it's got more electrons. And the end that has temporarily got slightly fewer electrons becomes more positive, and we get what's called a dipole. Now when that happens near an alkene double bond, the electrons here go, ooh, hang on a second, there's something over there with not enough electrons. You know what, let's go over there. And so over there they go. They all wander over and they stick onto bromine. Now, stick onto bromine is not quite right, they form a chemical bond, and in fact, if I was doing this, I'm going to just colour how this should be done, because whoever wrote this PowerPoint not wrote the PowerPoint, but wrote that image, was not the world's best organic chemist, because you should not be drawing those electrons moving onto the bromine. Those electrons should be moving to form a bond between a carbon and the bromine. So let's put that back in slightly more accurate. So the electrons go from here and they form a bond there between the bromine and the carbon. So that's forming a new bond here, basically. I'm just going to rub that out because you don't draw the bond there. So curly arrow to here between the curly arrow to here between the carbon and the bromine to form a new covalent bond. Now the electrons that were in the bond between the bromine and the bromine are now like, oh hang on a second, this bromine's got too many electrons, it's just gained an extra 2 from that covalent bond. Right lads, we're out of here, let's go and sit on this bromine. And bromine is perfectly good at accepting extra electrons. Its natural state is bromide ion anyway, so it just becomes a bromide ion, a full-on proper bromide ion. Oops, I just drawn over its negative charge. Here it is. And that's just going to float around as a minus. Now the slightly odd thing is the carbon, and I've actually drawn it attached into the wrong carbon here, so just to pretend that bond formed there instead. That's wrong, just convention of drawing. Now after that first bromine has stuck to this carbon here, lots of scribbling just to be really helpful, that leaves the second carbon, whose electrons just went for a wander to form a new bond, without enough electrons. So that carbon's actually formed a plus ion. We call this a carbocation. Now the bromine sees this carbon cation, it's got a lone pair, it's got spare electrons, it goes, oh, hello, I'm going to give you my electrons again. Just to be finicky, it wouldn't actually put its electrons onto the carbon, it would form its electrons into a bond between it and the carbon, which is a more accurate way of drawing it, and therefore forms a new covalent bond there. Now, as I say, that's a little bit mad, and I've just scribbled on it a lot, and at one point draw an arrow, or drew a line in a slightly unhelpful place, but it doesn't, oh, I've just rubbed out the white, never mind. It doesn't matter too much, you don't need to know the mechanisms yet. If you do A-level chemistry, then they become important, but they're not horrendously complicated. They're just electrons go here, electrons go here. We form a carbon plus and a bromide minus. Electrons go between them, form a new bond, and we end up with a situation where we used to have an alkene here, and we don't anymore. We've now got 2 more single bonds, making it an alkane, both to one of the things that were attached in the original molecule. Hopefully, if you enjoyed that mechanism, yay, you might be a proper chemist. You're all proper chemists anyway, please ignore that statement. But you might get excited about organic chemistry in a way that I didn't do at GCSE and A-level. Nowadays, I quite like it, it's rather fun. However, not really GCSE, so that is just extra. Extra. So I will move on and get back to what you actually need to know. Okay, sorry about that. I was just distracted by my family returning from a walk and Tesco delivery arriving, so I'll just move on and carry on from here. This first little task is a little activity, and what I'd like you to do is see if you can work out the formulae to complete the equations, or the diagrams in the case of the first one, because that is a display formula showing all of the bonds and all the atoms and their relative positions, and try and work out the names, if you can, of each of the products. So let's have a quick look. Pause if you want to have a go without any guidance, otherwise I will carry on. Okay, so the first thing I'm going to check is the names. And this, of course, is a 3-carbon chain and a double bond, so that's propene. Just to check the others, 4 carbons, so C4H8 is butene, C2H4 is ethene, and C3H6 is propene again. That's just the same as that top one. So we're adding bromine to the first one. Again, pause if the names are more helpful to you, but let's get it drawn out. So the double bond opens, and we're going to end up with a C, single on C, where the double bond used to be, with a hydrogen and a hydrogen. Again, apologies for the quality of drawing. And there's where the hydrogen was, and then we have the C, H, H, H. This is hard on a mouse with hydrogen. Ooh, that was a bit of a wonky one, sorry. They're all hydrogens, honest. Now we've added our 2 bromines, so there's one, and there's another. So that's all of the bromines present, and I've got 2 bromines on an alkene, an alkane. So 1, 2, 3 carbons. This is going to be a prop. Whenever you're naming stuff, you always start with the main chain of carbons. So prop is 3. There's no double bond, so it's an ane. Now we're going to look at the prefix of the name, which is the presence of 2 bromos. So it's going to be bromo. Ooh, that's hard to write. So bromopropane, but there are 2 of them. 1, 2. So it's going to be di. Ooh, see if I can make that I look a little bit better. So that is honestly a dibromopropane as written by whiteboard pen with a mouse, or projector pen with a mouse. Dibromopropane. Oh, for some reason my resin mouse doesn't really like some of the features of my photographed mouse mat, which is a picture of us at the seaside. Okay, so dibromopropane. Okay, let's get rid of that because it takes up far too much space and see if we can work out those. So, next one I've got is C4H8. Well, this isn't a display formula, so it's actually less effort than a Br2. So this is going to be C4H8Br2. Now we don't need to worry too much about the actual display formula for that. I mean, feel free to, if you want to extend yourselves, draw out the display formula and do that whole reaction like the top one for each of these. We can just name that C4H8Br2, or I know it's butene, so it's going to be dibromobutane. Oops. Again, it's now an ane, of course, because we have no double bond left, because the double bond's broken open to add the two bromines, and that is with two bromines. The next one I might dispense with the writing of the formula out. Sorry, not the name out. C2H4Cl2. Again, not saying where those are located, just saying they're there, because these are what we call molecular formulae. They're not telling us anything about the structure. We don't know where things go. And that's going to be dichloroethane. Sorry about the child describing the tractor in the background, apologies. And the last one is, well, it was propene, and it's going to have two iodine added. It's going to be C3H6I2, which is going to be diiodo. I didn't write down dichloro, did I? I said I was going to dispense with that. I might write down diiodo because that's going to be hard to spell. Diiodo. I-O-D-O. Diiodo. And then that's propane. That honestly is an L, oh dear. That honestly was an M then an E. My handwriting is terrible, but this mouse makes it rather, oh, that's slightly better, rather worse even than it is on a whiteboard. That's diiodo. Yeah, there are two I's in a row there. Diiodo propane. Maybe that I look a little bit more like an I. So, that was dichloro, C-H-L-O-R-O, dichloropropane. No, dichloroethane. Check the question, Mr. Land. Okay, moving on. Sorry I haven't written all of those out. I just think you might have suffered less from not writing the dichloroethane out. Next part. So, the next addition reaction is not halogens, but hydrogen. Hydrogen itself is very small and always has the potential to become slightly positive in the same way that the halogens do. So we can actually add hydrogen to alkenes, and we call this process hydrogenation. Now this might sound unfamiliar at first, but what do you think margarine is? Oh yes, hydrogenated vegetable oil. So vegetable oils like oilseed rape oil and sunflower oil tend to be unsaturates, and what we can do is we can turn them into saturates by adding hydrogen, and we do this at 60 degrees C with a nickel catalyst in the presence of hydrogen. So this takes our alkene, opens up that double bond, adding hydrogen to make an alkane. And this can be done usefully, but can be a useful thing to do. It's ethane plus hydrogen, ethene plus hydrogen makes ethane. So, questions for you. Why would you want to turn alkene into an alkane? You can Google it quickly if you want to, have a couple of minutes, or not. Let's have a look at the answers we've got. Unsaturated, saturated is obvious. What are the advantages and disadvantages? So, 1. Straightens the molecules. That could be considered a good thing. It increases the melting point. I appreciate that the Italians love olive oil on bread, but we tend to want to spread our fats onto our bread products, so we tend to like margarines and butter over olive oil. Just a taste thing, I guess. And then we have a specific example being hydrogenation. So if you add a certain amount of hydrogen, you can control the degree of spreadability. You can control the degree of, well, viscosity, let's be honest. And if you add too much hydrogen, it can go really quite hard. like butter. But if you don't add quite enough, or if you add exactly the right amount, you can make it so it's always soft and spreadable, but also not ever too runny, and also not ever too hard. So you can control the degree of spreadableness, its viscosity, by controlling the amount of hydrogen you add across the molecules. So, interesting. I wonder if you found anything else interesting that you could send to me as an example of what you found. Okay, 6 marks. 6-mark question. Unsaturated fats can be changed into saturated fats by process of hydrogenation. Describe the process of hydrogenation and evaluate the advantages and disadvantages of converting unsaturated fats into saturated. Give yourselves 6 minutes. Make sure you make at least 6 points, and the mark scheme will be up in 6 minutes' time, or actually about 10 seconds' time, because you're going to pause me. Don't forget, and I appreciate you probably just paused me so you're going to hear this afterwards, good English, and make sure you organise information clearly using specialist terms. Go! Okay, you've unpaused. Moving on. So, we're not peer marking today because you're on your own. Unless you can bully a member of the family to mark you, I'd like you to self-mark this. The criteria will appear in a second. You can give yourself a what went well, or an even better if, that would be nice, but let's focus on the getting the marks right straight off. Of course, you're going to be submitting to this to me as part of your work, and therefore I'm going to be able to give you an even better if and a what went well as well. So you have a go at marking it. I would like to see this as your homework, or as part of your homework, and I will give you feedback on this when I read the answers. Have a go in green pen at the marking. So, marking points for you to have a go at green penny, and I will of course refer to this when I mark the final version. 1 to 2 marks if you get, and I appreciate that it says D there, it doesn't mean that at all. That's like 4, 5, or 3, 4. CB ball band, so let's call it 6, 7. Not quite right. AA star is 8, 9. That'll do. Ooh, my pen went weird again there. I think that's top left corner, the top right corner of my mouse mat doesn't really like a 4. Do. Okay, so you give an advantage or a disadvantage. You've included some errors in spelling, punctuation, or grammar. That's always the hard thing to spot when you've written it yourself. A good description of hydrogenation. So we'll look for the key points down here for good or simple. A good description includes at least 2 of those key points. And you've given an advantage and a disadvantage. And grammar is fine. Excellent description, we're looking for all 4 of those points, with an advantage and a disadvantage given and evaluated. That means you've made a decision. No mistakes in spelling, punctuation, or grammar. So, key points. Addition of hydrogen across double bond, or mark. Replaces the carbon double bond for a carbon single bond. Transition from unsaturated to saturated. Context of a nickel catalyst at 60 degrees C. That would normally be 2 marks in the exam question, but there's a lot going on in this one. And increase in the melting point, so become solid at room temperatures. Disadvantages. Saturated fats tend to be a less healthy option because you fit more fats into the body and you can make it harder for the body to break them down. Advantages. It's now solid, so it's more spreadable and it's more useful in terms of storage, motion, and where you can put it. That last one, I mean, seriously. Okay, give yourselves a mark out of 6. Put it clearly on your working green pen so that I can also have a look and see if I agree. Moving on. So, our third addition reaction, we've already added the halogens and hydrogen. We're now adding water. So we can also add water across the bond, because water is always polar. It's a permanently polar molecule because of the difference in electronegativity between oxygen, which is very good at grabbing electrons, and hydrogen, which is not. So hydrogen's always a little bit plus, so they're very good at attacking the electron-dense double bond, and so you can fairly easily add water across. Now, I say fairly easily. You have to have a concentrated phosphoric acid catalyst, and it has to be under high temperature and pressure. We call this reaction hydration, which makes sense. You hydrate when you add water, right? So let's have a look at it. Here's our alkene. We add water, and we form this monster. Now, this bit over here, that's the functional group for a new group of well, they're not hydrocarbons, organic chemicals. A new functional group means a new homologous series. We've had the alkanes, all the most boring possible hydrocarbons. We've had the alkenes, the unsaturated hydrocarbon double bonds. Sorry about that, some of this is murdering my 1 year old. And now we have met the alcohols. Yes, this is ethanol. This is the thing that you shouldn't drink because it will make you drunk and damage your brain. So there's ethene, there's water, and there's ethanol. We will meet the alcohols in more detail in the future. But just like you have methane, ethane, propane, and butane, you have methanol, ethanol, propanol, and butanol. And we'll come back to those, well, next lesson. Okay, moving on. Now, this reaction is reversible, so you can actually break ethanol back down into ethene, which is a little bit tricky to do. Conditions are interesting, and in order to make this reaction more efficient, this is slightly equilibrium-y stuff, you can recycle the unused parts and therefore control your yield in a better way, a bit like the Harvard process. Now, this is a little interesting feature. Again, this is a bit A-level, you don't really need to know this, but you know, it's an interesting feature. Here we have a propene molecule with a double bond and a single bond, and here's our water. Now, everything we've seen so far when we've been adding has been symmetrical, but when I add my water to propene, I've got an interesting situation. And the interesting situation is the asymmetry of this molecule. Those are the two things that are going to attach. That hydrogen attaches first, and then that OH plugs on somewhere else. So the question is, am I going to get this molecule, and well done if you worked this out as the problem, and I'm just not going to draw all the H's for brevity, and then OH there. Again, at GCSE I'm supposed to put the bond in between the OH, but that's not actually commonly done anywhere else in the world. Organic chemists tend to assume the bond between the oxygen and the hydrogen, so I will often forget that when I'm doing the writing on the whiteboards here, and I'm just going to ignore the hydrogens. I'm not doing a full skeletal, I'm just not drawing them all in to save your lives. You're having to watch me draw, in that case, 6 hydrogens, which is more than necessary. Okay, I could put the OH in the middle, where the first hydrogen bonds to this carbon, we'll call it carbon 1, and then the OH bonds onto carbon 2, and the carbon 3 stays as it is. Or, the first hydrogen might stick onto carbon 2, and then the OH sticks onto carbon 1, which would form this molecule. As I said, very A-level this stuff. So here's the hydrogen we've added. I should really put the hydrogen we added on here. And then the OH we added goes here. Hydroxide group. So as you can see, those are actually 2 different molecules. And at A-level, you'd learn to number them. You'd also learn, oops, extra way of drawing them up for no good reason. You'd also need to learn that you get what's called a major product and a minor product. At A-level, I'd expect you to know why we get more of this one and less of this one. But at GCSE, you may as well just know that this one is what's called the major product. About 2/3, 60–70% of that will form this one. And it's because this carbon here is better at being a carbon plus ion than this carbon here. Because this one has got a methyl group next to it, whereas that one doesn't. The methyl groups push electron density onto the carbon, stabilising carbocations. But like I say, A-level, not really something you should worry about. It's just an interesting extra thing. So we get this product over that product 60–70% of the time. One of the bottom here says, do you think there's going to be a similar problem for this one? Have a pause, have a think. Hopefully, your answer was no, because that is symmetrical. Yes, you've got carbon 1, 2, 3, and 4, but my numbering here is entirely arbitrary. I've just decided to write 1, 2, 3, and 4, rather than 1, 2, 3, and 4. If I flip the molecule around, it's exactly the same. So putting the OH here, the only difference between putting it there and there is which way around I've got the molecule. So those are identical. And there is absolutely no difference in those 2 positions, and then I just number the carbons based on which one of these, which one was closest to the end, which one had this one closest to the end. So that one won't get 2 different carbons. It's only the odd alkane or alkenes that will produce us with a major and a minor product, or an asymmetrical one. So you can put it there, then you get a major and a minor product, but not if the double bond is central. Moving on. Apparently I didn't animate up all the pluses and arrows. Nice. Okay, the last addition reaction you need to know about is going to go into a lot more detail in the next little subtopic on polymers. You did this in either year 9 or year 10 when you did giant covalent molecules, and I'm going to do a very, very quick précis now, because we will come on to it in the next subtopic anyway. So the other thing alkenes can do is undergo addition reaction with each other. So if I have multiple alkenes, they can all open up their double bonds and form new single bonds between them. And this forms long molecules called polymers. Now I've got a really silly way of remembering how to draw this, which we'll do on the next slide. Okay, so the notation for polymerization is actually a bit fussy. So here's the alkene, and here's the N. That N means, rather than writing out several alkenes, that just means an unlimited number or an extremely large number of alkenes. Now, I've got a silly way of remembering how to draw alkenes, and I call it, it's from a film that you may or may not have watched. I don't recommend the film in any way. It's a Riches to Riches story with a bright, intelligent girl who's also good looking becomes a bright, intelligent lawyer who's also good looking, but she decides to use her massive fortune. Oh yeah, I forgot to mention rich in both sides of the sentence, so it's a Riches to Riches story who decides to go into animal cruelty or something for her. Anyway, you don't have to go and watch it, but the key phrase I'm using is bend and snap. Fans of Legally Blonde, you can stop cheering now. So why I use this for addition polymerization is to avoid you getting massively confused. Because the alkenes often are drawn either like this, with their bonds sticking out at a funny angle, in which case they're a little bit in the way, and that's not too bad, or they can be drawn like this, and this is particularly bad if you've got extra alkyl groups at the end of the chains. So you could have bonds going up or down, and then left and right. I'm trying to draw polymers of this, and I haven't drawn that very well, sorry. It can be a bit difficult because there's no obviously to put the continuing bonds. So bend, which I'm going to circle in blue now, is the step one, and it's get everything out of the way of the double bond carbons, because this carbon and this carbon are what are going to do polymerization. So these bits need to not be here. So we're going to move those down here. Just going to bend, because covalent bonds actually aren't 90 degrees as we've drawn them here. In 3D they're a bit more complicated than this. So I'm going to move them down out of the way because it's more convenient. Now apologies, I'm not going to leave this on the whiteboard, I haven't got space to leave that up there. So I'm going to get rid of those hydrogens and leave them at the bottom. So all I've done is I've redrawn it so they're out of the way. So that's the first step, that's bend. The second step is snap. Now snapping is the breaking of one covalent bond and the forming of two new covalent bonds. Well, one each for the carbon, so effectively one electron goes there, one electron goes to there. Let's get rid of those two lines because you don't use mechanism stuff. And let's get rid of that covalent bond, and there we have it. So these two have formed covalent bonds that now pass through the way we draw polymer notation. We draw polymer notation as a big bracket there to say all of this over and over again, and we use a number little m there to say many copies of this. So this is the repeating unit. There's my light highlighter. This is the repeating unit, and there's n of those monomers, so there's now n of these polymers. So this chain goes on and on and on and on forever, but to save drawing it, we just draw one repeating unit. And I know I've put CH3 up there, that was just an example, to make it correct for this. There we go. That's now correct for the monomer I started with, because the monomer I started with is hydrogen, hydrogen, hydrogen. And this should be hydrogen, hydrogen, hydrogen. I was just trying to show you something that would be more difficult with something else on there. That I'm sure confused some of you, so apologies. It should always have been a hydrogen to be accurate with this. So, bend to get stuff out of the way from either side of a carbon-carbon double bond, and snap breaks open the carbon double bond and goes through the brackets. We'll do more on these later, so sorry if that's caused you any. No. Okay, summary of all addition reactions. You can add bromine, chlorine, iodine, etc. And one molecule can neatly add over one double bond. You can add hydrogen, which is exactly the same concept. Open the double bond, add hydrogen on. Nickel catalyst required for this one, and 60 degrees C. You can add water, where you need steam and phosphoric acid. And you can add other alkenes to form addition polymers. Now, how those form depend, or conditions those require, depend on the polymer you're making, the monomers you're using. So that's something we'll look at in more detail in polymers. So, then we get to naming. Now, we've mentioned the naming again. Dibromo, dichloro, diiodo. Hydration makes enes into anes. Hydrogenation makes enes into anes, and hydration we'll do next lesson. Also, the polymers we'll do in future, but basically whatever the monomer was in addition to polymerization, you've just put poly in front of the monomer name, and that's your polymer. So we saw ethene earlier, and that will become polyethene or polythene for short. Now there's a short quiz coming up. I'm going to flash through it and give you some marks at the end. Feel free to have a go at this. Again, if you want to do it as a competitive thing, mark yourself and submit that as part of your assessed work. Moving on. So, 1 to 9 looks, again, let's ignore the A stars because that's not relevant. If you get a 9 out of 9, we'll call that a 9. How about that? And again, 7 out of 9, we'll call it a 7. There we go. Out of 9 for grading. How convenient. Okay. There are going to be 20 seconds on each slide. I will read them, but do nothing else. Actually, they may not change automatically. We'll find out. Ooh, noise effect, sound effects. Addition of water is called halogenation, hydrogenation, hydration, or hydrogenation. Please don't listen to me, read the words. I wonder if that's 20 seconds yet. I'll give it a little bit longer and then move on if it isn't. Ooh. Yep, that's definitely over 20 seconds, so moving on. Question 2. Benefits of hydrogenation. Changes the melting points, making fat healthier, adding more hydrogen. One of those is probably the right answer even. Question 3. Is that saturated or unsaturated? Well, it's exciting. Hopefully you've written the answer. Only got a choice of 2. Can this molecule undergo addition reactions? And why, if it can, or why not if it can't? Although I believe that might have given you the answer away already. I probably ought to go a bit slower, right? Shout louder, I can't hear you. Shout back in time there as well. Okay, what is the definition of a functional group? Well, I've mentioned this, but I haven't done it explicitly, so I wonder if you're getting some right. Got a family of organic molecules of the same functional group. That doesn't sound like a good definition of it. Family of organic molecules of characteristic reactions. Or a compound consisting of just hydrogen and carbon. Well, I've got to be honest, I wouldn't define it using any of those, so, interesting. Yeah, okay, fair enough, one of those is actually definitely right if I've read it properly. So I'll avoid confusing you further. One of those is definitely right. One of them is related, but obviously related, and one of those is just not the right answer. Moving on. Ooh, a structure, if bromine water is added to the molecule below, you've got another 13 seconds. It's going to take you at least 13 seconds just to draw that, so I suggest pausing and giving yourself a bit more time on question 6, don't you? So bromine water. Bromine water is bromine, the key thing you're looking for there. The water is irrelevant. It's just bromine. Br2. You're forming something. I'll stop giving hints now. Dibromo. Moving on. Structure of bromine water is added to the molecule below. Well, yeah, I can see why you're asking that question, but it's not a nice question because it's a bit cheeky. This one's very quick to draw. Well, no, you still got to draw it, I guess. Oh, there we are, that's more than 20 seconds. Moving on again. Question 8. Ooh, 2 structures if we add water to the molecule below. I can't remember doing this about 4 or 5 minutes ago. Hopefully you remember it. Maybe not. I do want both structures to get the marks. But you know what? I'm not going to give you answers on this PowerPoint, am I? You're going to have to give me the answers as the homework. Okay. Pause if you haven't done that yet. And the last question. Why do you not get 2 different structures when this reacts with bromine, only when it reacts with water? Give me your written answer. That's your A-star grade boundary question, or your 9 grade boundary question. Let's be honest, I need to update the numbers in the PowerPoint. I did not notice that until I started recording. So apologies for the slightly misleading numbers and my poor help in one of the questions. And by that I mean seeming to actively make it harder than it needs to be. Right, I'm on the last slide. You're probably on your last legs. Please submit those 9 questions as part of your homework, along with the 6 marker and the 4 marker. Why not? Hopefully you mark the 4 marker yourselves, so I can just see. The 6 marker I'll give feedback on, and I'll tell you the answers for the 9. particularly if you send them to me as a document, a Word document that's nice and easy to edit or print screen into a Word document for you. Either way, you'll get some kind of feedback. I hope that was not too soul-destroying. I'm going to go and encode it now and then put it on to show my homework. Thank you ever so much for listening. Take care, stay safe, and you'll hear me next week, and I will, except for those who I haven't yet done ARD meetings with, won't see you all for quite a while, I suspect, which is rather sad, but hopefully September, if not before. Bye.